Okay, so we're going to start now with the second part of lesson 18. The third part I'm going to release on Tuesday in advance of Wednesday's lecture. What we're going to focus on today is one step of this, which is figuring out how to find what we're going to call a simplex direction. And this is going to be a specific form of a feasible direction. The idea so far is that in the general improving search, which is written here, we're at a point x naught, a vector x naught, and we want to find a direction and the step so that the direction is feasible and improving. And then the next iterate, in this case x1, if we started at x0, would be x0 plus the step, lambda, times its direction. Okay, and in that way, this new solution has a better objective value than the previous. Okay. Once we turn this into the simplex method, the point is that the x iterates, so x0, x1, x2, and so on, are going to be BFSs, basic feasible solutions, i.e. extreme points. That's why we've been spending all this time in the previous few lectures talking about what an extreme point is, what a basic feasible solution is in canonical form. Today, we're going to really cast back to what we were doing with improving directions to talk about what are simplex directions. So our D that we use are all going to be simplex directions. Okay, so we're going to talk about that, and after this video, the assessment for this video is going to have you do a very similar computation to the one I do. Okay, through this lesson, we are going to be using the canonical form listed below. You should note this is in the textbook too, so you can look there as well for an additional way of thinking about this. We have this canonical form linear program. We know it's canonical form. It has all equality constraints and non-negative variables. As with any linear program, negative. You should start, I think, by looking at this, and once you observe its canonical form, you can think about, well, the number of decision variables is n. Here that equals 5. The number of equality constraints is 3. Okay. Those are important numbers to consider because from there we can generate some understanding of what we're looking for. So the first thing we're going to think about is our initial basic feasible solution. One thing you might look and notice at right away is the particular structure of these last 3 columns. That kind of structure is really useful when we want to find an initial basic feasible solution because you can see that if we held these variables equal to 0, then the solution is going to be read off as just S1 equal 24, S2 equal 24, S3 equal 23. So I hope that's obvious to you that that is indeed a unique and feasible solution to that system of equations and inequalities. I'm going to formalize that just a little, just putting it back into the language that we've been talking about it. But that's exactly what this is saying right here. We're starting with this sort of clear solution. We have we can use our theorem about canonical form, or you can use the definition of basic solution to verify first that x naught is a basic solution. I first note that the equality constraints are satisfied. That's what this bit just really verified. Second, I'm going to note that the columns associated with the constraints, or with the variables S1, S2, S3, it form the following matrix. Okay, so we need to verify that these columns, or the matrix formed by these columns, are linearly independent. Note that I got that from this. Okay? The determinant of B is equal to 1. Why? Well, you can see that's true just from either calculating in Python or just recognizing that B is the identity matrix. Okay, so we have a set of linearly independent columns corresponding to our basic variables. We have the equality constraints are satisfied, and we have exactly 2 non-basic variables. Those are set equal to 0. Remember, we know this must be 2 because it's n minus m non-basic variables. Set to 0. Note this is just another way of saying we have 2 active non-negativity constraints. Note how that corresponds to the 3 active equality constraints, or in other words, 3 satisfied equality constraints. That makes a total of 5. That really gets you back to the definition. Of course, the theorem lets us know that these are linearly independent by just looking at the columns. And of course, if you formed the matrix, if you wanted to use the original the definition of basic solution, you could too by forming the appropriate matrix. You would note that that determinant is either 1 or -1. Anyway, so now we know we're basic. We're also can note that I'm going to put that vector bar over x0 so we understand it's a vector. x0 is also feasible. We knew the equality constraints are satisfied. And if you just look at the components by examination, we know they're all non-negative. Okay. Thus, x naught is a basic feasible solution. And of course, by the theorem that we know, that means that x naught or x0 is an extreme point. Okay, so because it's an extreme point, that means the situation is that it's sitting at, and the other thing is because n minus m equals 2, we are sitting in a 2-dimensional space. If you wonder why that is, it's because we're sitting in 5-dimensional space, but we have to satisfy 3 equality constraints. That reduces the dimension to 2. So we're actually in a 2-dimensional plane. We want to know there should be 2 directions, 1 on each of the constraints leading from x0. And what we want to figure out is how do we calculate what the algebraic characterization of these two directions are. We're going to call one of them dx and the other is dy. I will calculate dx, and then the assessment is going to ask you to calculate dy. Okay? So, how do we start this? We want to move in so that we go to an adjacent. We want to point in the direction of an adjacent basic feasible solution. Okay? In that case, what it means is that n minus 1 active constraints must be the same. Okay, so between x0 and x1, wherever we move next, they have to share n minus 1 active constraints. Well, let's think about what these can be composed of. The three equality constraints always must be shared because we have to satisfy both. They're both basic solutions. They have to satisfy all equality constraints. Thus, they must have one common. There are two constraints left, so one of them must be common. When I say two constraints less, I mean two active constraints less. So they must have one common active non-negativity. Okay, so then let's think about that. We're going to take one of our non-basic variables and we're going to make it basic, and then that's going to remove one of the basic variables out of it if we step far enough. Okay, so this is the step size calculation. And this is going to turn out to be the simplex direction. Okay, so we're going to think about that first. We're going to suppose we want to put one non-basic variable into the basis. And that's going to be boiled down to calculating the simplex direction. Don't confuse, when we say y here, we mean any variable y, not just the particular for example. And this direction that we calculate, it has to have a component for every decision variable, and that's going to respond to what the action is on that variable so that we can move in this space. So that's going to be this direction here. It's going to be here or here, and it's going to be geometrically corresponding to where we are pointing in this case, in the 5-dimensional space. Well, let's think about just the non-basic variables for a second. We only want to affect one of them, and the rest we don't want to affect. In particular, for this example, we want to affect one variable, and we don't want to affect the other variable. We want to either affect x and not y, or we want to affect y and not x, since those are our two non-basic variables. So we set the one we want to affect to 1, and the other non-basic variables we set to 0 for that direction. When we do this calculation of x1, you see that what that's going to do is, remember, it's going to start at x0 and it's going to add to it this simplex direction. This is going to be a component by component addition. We'll only change the y non-basic. All other non-basics will be unaffected by this direction. And then, of course, the question is what about the basic components of D? Okay, for that, we're going to rely on the fact that this thing that we calculated for improving directions, so we did this in a lesson 11 and 12. Okay, and I'll write down the algebra for it right now. What we have here is AX. So this, you're going to note that this, well, forget about the non-negativity for right now. Just think about the equality constraints. The equality constraints must be satisfied. And right now, we have them satisfied by AX0. In other words, AX0 equals the B vector. Okay, we're going to move to X1 is going to be equal to AX, not AX, what did I say? We're going to move to X0 plus lambda D of y. Okay, we don't know what lambda is, but we do know, and we'll worry about that next time, we do know that AX1 equals B must also be true. So if that must be true, we can think about, through substitution, ax0 plus lambda dy must also equal b. Distribution says that ax0 plus lambda dy, lambda a dy, well, that equals, remember, this equals b plus lambda a dy must equal b. Of course, the b's cancel out. The lambda, as long as it's not equal to 0, which it won't be, it'll be positive, it can be divided out, and we have a dy must equal 0. And here it's the 0 vector. Okay? And that's this part of what we developed. Equality constraints, your direction can't change any of the equality constraints. Since we have the equality constraints being defined by this A matrix, remember that's the coefficients of the equality constraints, we have this formula to use to help us. Now, we have this over here. Note that for our non-negativity constraints, we must have dy of z be not non-negative for all non-basic variables. And this formula does ensure that. Okay, we can choose anything non-negative. We happen to choose these so that we only affect one of the non-basics, since we set everything else to equal to 0. That does satisfy the non-negativity required. Okay, so how does this work in an example? Like I said, I'm going to do one of them. I'll do dx. And then on the assessment, I'm going to ask you to calculate dy. You're going to note that the calculations are almost identical. There's just one change in the calculations. So to start off with, I think, okay, I want to calculate out dy, which is equal to I'm doing dx. You guys are going to do dy. So this is dxx, the first component. dxy is the second component. dxs1 is the third, and so on. Note that the superscript indicates which non-basic variable is being changed by this direction, and the subscripts refer to the components being affected in the solution. Okay, we will choose dxx equal to 1 and dxy equal to 0. And that's okay to do, because we have freedom to choose whatever direction we want. We just want to make sure that we're only affecting one non-basic variable. We have to make it positive because our variables have to be non-negative. So we couldn't make it negative, or we would be leaving the feasible region. Okay, so we choose that. This is going to be part of the way of moving along this edge direction. Now we think, all right, we need a dx equal to 0. Okay, in other words, ADX, this is basically substituting components of dx into the constraints. Remember, that's what ADX, A times any vector, is just the left-hand sides of all the constraints. And I can spell into, honestly. Okay, so what is this? Well, I mean, I can just look back at the constraints here. And basically everywhere I see x, y, s1, s2, s3, I just put in these components that I have for this direction. So it's going to be 4. It's 3 equations. It's 4 dxx plus, I believe it's 3. No, plus 1 dxy plus dx S1 equals 0. Next line is dxx plus, I believe it's 3 dxy plus dxs2 equals 0. And then 3 dxx plus 2 dxy plus dxs3 equals 0. I do substitution with these guys into here. And so then I see that this is the same thing. So dxy is 0, dxx is 1, so this is just 4 plus x s1, 1 plus dx s2, and 3 plus dx s3. And they're all equal to 0. It's a 3x3 system with a solution I can actually write down. It's dx s1 equals -4, dx s2 equals -1, and dx s3 equals -3. And of course that means that dx vector equals 1, 0, -4, -1, -3. And you can check. This does satisfy the condition that a dx equals the 0 vector. So it'll be, a dx will be, remember when I say the 0 vector here, I mean 0, 0, 0. And also, dx x is non-negative and dxy is non-negative. Thus, dx is a feasible direction. You can check this. It must be true by the way in which we calculate it, by the way. You don't have to check this after you calculate it correctly, but it is a feasible direction. And in particular, this is a simplex direction, one of the two simplex directions. Okay, so I'm going to stop here. And for the assessment, I want you to calculate dy at this x0.